All right, so let's continue. All right, so we see the problem. So we have intuitively we see the if we have degenerate case, and we immediately see that I have in perturbation theory I learned before I have this 1/0, which is not good. So which means this formula we learned before, this formula applied to non-degenerate case. Okay. Right. So now let's deal with the degenerate case. Right. And then before we do the formal derivation, let's see some simple example. Very simple example. And for example, I have the H naught, the Hamiltonian, which is E and E. So therefore, I know that I got two states. Because this is already diagonal, right? This matrix is already diagonal. H naught is diagonal. So I can immediately see that there I have two eigenstates. I call it 1 and like 0 equals 1, 0, right? And eigenstate 1, 0 and another eigenstate I call it 2, 0, 1. And obviously, these two states have energy E. The same energy E because diagonal, right? Okay, which means by H naught 1 E 1 and H naught 2 equals E 2. So I have two degenerate states. And now, if I add the perturbation, for example, if we add a perturbation, H1 equals say 0 lambda, okay. 0 lambda and lambda is added. So according to the formula we learned, according to the EN1 before. You see that my n equals 1 0 1 1 0 or okay, if I calculate the energy correction to the first state, and this is my formula I learned before, right? So when you plug this in on found, I find that 1 0 0 lambda 0, and this is 1 0. And you immediately see this is 0 lambda 1 0. Of course, this is 0. And the energy correction to the second state, again, you can see this is 0 too. Okay. So it doesn't really break the degeneracy. Doesn't break the degeneracy. And on the other hand, we can solve this energy precisely. Now the H equals H naught not H1. H naught plus H1, and you can write it down. This is E lambda T. So our eigenvalue equation, we can run it H. Well, what's my notation? Can I write it? Okay. N. I use this N as a subscript to distinguish two states, because now it's a 2 by 2, so I immediately see that we have two states and two eigenvalues. So I can write it So my eigenvalue En equals. So in order to solve for En, so I say determinant H minus En equals 0, right? I solve all this eigenvalue. And this is easy because this is 2 by 2, which means E minus En lambda E lambda E minus En equals 0. Okay. And then so E minus En squared minus lambda squared equals 0. Obviously, I can solve for En. En is E plus or minus lambda. Okay, then I take 1 E plus lambda, E2, E minus lambda. So which means this state or this perturbation indeed breaks the degeneracy. Break the degeneracy. Okay. So I have an E over here, and I have 2 states. So now, before the perturbation, I have E over here, but I have 2 states in this energy level. And after I apply the perturbation H1, and one of the states goes to here, raised up by lambda, and another state goes down by lambda. So they shall go to E plus lambda, E minus lambda. So the degeneracy is broken, right? Okay, so let me pause a little bit. We have a simple Hamiltonian, non-perturbative Hamiltonian and the perturbation together. And without the perturbation, we have the degeneracy, 240 degeneracy. And if we use the formula we derived before, obviously the correction to the energy is 0. Okay, and then you may say, well, you are calculating the first order. Maybe there's a correction for the in the higher order, right? Okay, you just calculate the first order, but is that true? 也许你会说这个我们如果用之前的方法呢，我就把这个套进去，然后算完之后就是0，一阶修正，一阶修正是0，那你就说，哎，那也许是一阶修正是0啊，也许高阶修正它不为0啊，这个 degeneracy 这个减轻还是被打破了，不是吗？对不对？你也许会这样想，但是你注意看，这个是我们实际上不管它这个我们没有用任何的这个微扰理论嘛，对不对？这是实际上去解它的嘛，对吧？实际上解出来的结果呢，它的 eigenvalue 呢，它的 eigenvalue 呢，你看从1变成了2个，1加 lambda 跟1减 lambda， 那这个 correction 是多少？修正了多少？修正了 lambda 的几次方 ？lambda 的1次方啊，对不对？那我们在讲那个 perturbation 的时候，我们说这个能量或者是这个态呢，修正呢，order by order， 1阶修正、2阶修正、3阶修正，对吧？那个修正的量跟我那个 perturbation 的一个 parameter 乘什么？跟那个次方一样啊。我若里面有一个，我若那个修正的 perturbation 那个 parameter 有个 lambda， 就像这边这个 lambda， 1阶修正的 order 就是 lambda， 2阶修正的 lambda， 2阶修正的那个量应该是多少？应该是跟 lambda 的平方嘛，有个 lambda 的平方。3阶修正有 lambda 的3次方，是吧 ？So it convinced me that the correction in the perturbation theory before it fails. It cannot give me the correct answer. Okay, so now it's really convinced you that we have to deal with the degenerate case separately. Okay, and now let's continue. In this case, we can solve the energy after the perturbation, which means we have the energy correction that is the order of lambda, and the degeneracy is broken. And not only that, we can also solve the eigenstate, right? Okay, so in this case, the eigenstate is E equals E plus lambda, or En. En equals E plus lambda, then I plug this in, I found it, plug into this equation, and N, I say is A and B, okay? So I just plug this in, I got E minus E plus lambda, E minus E plus lambda, AB equals 0. So we solve for it. This is equal to minus lambda, and then from that equation, you can see that we got A equals B. So I can define my first eigenstate is sorry, I correct my notation. I write this 1, maybe beta, E1, okay, and then this is 1. That's beta. So I can choose my A equals, and then I take A equals B equals 1. So the first state would be 1, 1. Right? And including the normalization condition, I have another factor 1 over square root 2 over there. So the first eigenstate I can choose is 1 over square root 2, 1, 1. All right? Then the second case, I call it E2. If E minus lambda the eigenstate. So I can say that E2 equals AB again. And I just plug it in, so I can get E minus E minus lambda, 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 E minus E minus lambda, AB equals 0. So here you can easily see that this is lambda, this is lambda, and that implies A equals minus B. So I take A equals 1, B equals minus 1. And I can write my 2 equals square root 2. It's a normalization factor. And 1 minus 1. This is my second eigenstate in this case. Okay, so well, I have summary, short summary. In this case, I have 1 equals square root 2. 2 equals square root 2. And with E1, E plus lambda, E2, E minus lambda. Well, but up to here, some of you may already notice that, well, actually, my 1, the state 1. The state 1, actually, you can write it right? Because at the beginning, we know that this is the state without the perturbation with the energy E, and this is another state has the same energy E, right, without the perturbation. And if you forget, I just remind you this I call it 1, 0. This is I call 0, 1. Isn't it? So actually 1 is the square root of 2, 1 plus 2 before the perturbation applied. The linear combination. And also the second state is the same. And also the linear combination. And because 1 and 2, in this case, 1 and 2 is the linear combination of the 1, 0 and 2, 0. The 1, 0 and 2, 0 are eigenstate of H0, right? Okay. So what happened? Because these two are eigenstate of H0, which means 1 and 2. One and 2 are eigenstate of H0 as well. Okay. Well, so the picture would be all like this. So now we have, instead of using 1 and 2, I can use, instead of using 1, 0 and 2, 0, I can choose 1 and 2 over here, and this is E. Of course, with energy eigenvalues. Eigenvalues E. And then this is degenerate. Right? 1 and 2 are also eigenstates, and 1 and 2 have the same energy, but 1 and 2, obviously, these two are different. So 1 and 2 are degenerate. Right? So in energy level, before the perturbation, H0, I have in this state, in this energy level, I have two states over here, 1 and 2. But after the H1 applied, my lambda. So now I goes to E plus lambda, E minus lambda. Therefore, after the perturbation applied, 1, 1 goes to here. and 2 goes to here. So 1 and 2 are separated. So H1 separate. 1 and 2. Right. Good. Okay. And not only that, and also H 1 0 lambda 0. This is of not diagonal. This is not diagonalized because when you choose this this form, we are using the basis. The basis 1 0 and 2 0, which is 1 0 and this is 0 1. This is not diagonalized in this basis, right? We are using this basis to do this H1. You're right. Use this. And but and now let's use another basis. I choose a 1 and 2 as basis. I use that instead of using 1 0 and 2 0 as the basis. Use these two bases, and this is the matrix form I got. And this is not diagonal. This right. But now, if I instead of using 1 0 2 0, I change the basis to 1 and 2. Okay, and now in this case, which means in this case, if I change the basis to 1 and 2, H naught stay unchanged. You all right? Why? I change the basis, then your matrix form should change, right? All the elements will change. But why? Even though I change from 1 0 to 2 0 to 1 and 2, but my H naught doesn't change. Why? Because 1 and 2 already the eigenstate of H naught as well, right? So in this case, even though I use these two state as a basis, H naught still diagonal. And what is the diagonal element? It's the eigenvalue, right? So it's still EE. It doesn't change because eigenvalue is E. 好，我现在 我现在之前做的全部都是就是跟你们之前习惯的，我用的 basis 是1001对吧？用这个 basis， 用这个当基体呢，做出来的这个 H1 呢，它的这个矩阵模式呢，矩阵形式看起来就是这个样子。那这个矩阵形式呢，基本上它不是对角化，是吧 ？OK， 好，那现在呢，我不要用这个当基底，我用什么当基底呢？我选另外一个当基底。那哪一个当基底呢？我用1跟2来当基底，可以吗 ？OK， 那我就来看，那我当基底是把1跟2当基底的时候呢，我的所有的这个operator 的那个矩阵形式、矩阵元应该都变掉了嘛，不是吗？因为我基底化的嘛。但在这个例子里面呢，即使我用1跟2当基底的时候，我的 H0还是没有变，为什么？为什么它还是不变？它的矩阵元还是不变，而且它还是对角化，为什么？因为1跟2它本身就是 H0的什么东西 ，eigenstate 嘛，而且它的 eigenvalue 就是1嘛，所以呢，当你用这个做基底的话 ，H0呢根本就不会改变，还是怎么样？1 1 0 1这样子，这样可以吗 ？OK， 那这个1呢？这个1呢，就是说这个呢就是第一个 state 0，第一个 state 1，第一个 state 第二个 state， 你如果不信的话，你去做，这都是0呢。所以呢，这个呢，你去做的话，这个就会等于这个，这个就等于它。我应该反过来写。Okay, not change. Okay. Oh, so H0 stay unchanged, but now how about H1? So how about H1? Okay. E1 and 2. So my H1 in this 1 and 2 equals to 1, H1. Okay, and then let's calculate one by one. Okay, so this is my H11, 1 equals 1, 1. So I got square root 2, 1, 1, 0, lambda, 0, square root 2, 1, 1. Right? Okay, so now I got 2 over here, 1/2, and then I got lambda, lambda. 1. So equals lambda. Okay. And second element, Second element, h1, 1, 2, 1, h1, 2 equals square root 2, 1, 1, 0, lambda, 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 0, square root 2, 1 minus 1. Easy, just a matrix operation equals 1 half and 1. So 1, 1, 0, so that's lambda, lambda again, but now goes to 1 minus 1. And this off diagonal element, matrix element equals 0. We are happy because it looks like we are diagonalizing this h1. 看起来你得到这个非对角线的元素，线是0的，对不对？那这时候你就觉得应该开始觉得有点开心啦，因为这个对角元素是0，这个非对角元素是0的时候，那这个是对角元素，对角元素不为0，非对角元素为0，表示说你正在把这个你选的这个基底呢，正在把这个 h1 怎么样对角化，这样可以吗 ？Okay, so we can do the similar things. h1 to 1 to h1. Okay, you can do that by yourself right now. So square root 2, and that's 1 minus 1, 0, lambda, square root 2, 1, 1, equals 1 half, and lambda, or minus lambda, lambda, 1, 1, 4, 0, yes, happy. And then, finally, two component, 2 h1, 2, so 1 half, square root 2, 1 minus 1, 0, lambda, 0, and square root 2, 1 minus 1 equals 1 half, and minus lambda, 1 minus 1, what you got? Minus lambda. OK， 那你22的这个 component 得到是负的 lambda。So finally, my h1, this perturbation in this basis, 1, 2 basis, goes to lambda 0, 0 minus lambda in 1, 2 basis. All right, so what we can learn up to now. So if I take 1 and 2 as a basis, if I do this, if I change the basis, my Hamiltonian one goes to minus lambda, which is diagonalized. already all diagonalized. And when you have the diagonalized Hamiltonian, what's the energy? It's pretty easy, right? Just the element in the diagonal. So when you see this Hamiltonian, you immediately see, okay, I have two different energies. One is E plus lambda, another one is E minus lambda. Okay, and also consistent because when we take off the perturbation, the energy level will go back to the situation before the perturbation, right? So whenever your lambda goes to 0, when this guy goes to 0 and 0, it goes back to the previous edge. What's that?所以本来是，所以是那个的原因，所以我现在越讲越大声，因为我觉得那有声音很吵的，但是没有吹，好像又有点闷的两难，那就开开关关吧，不然怎么办 ？Yeah, OK， 所以我就说这边呢，基本上就是非常的，你把它变。所以我们这边做了什么事情？其实只有做一件事情。如果我们做了很多事，但是最重要，我就告诉你一件事情，告诉哪一件事情？我们要选一个什么东西？好的 basis. We should choose a good basis, a nice basis. Okay, if I choose a good basis, and then my Hamiltonian will be diagonalized, and everything is easy. So the difficult part is that how to choose this good basis. All right, in the degenerate case. So in the degenerate case, we go back a little bit. Initially, we have the usual 1 and 2. These two states. Okay, but we change these two states to the new state 1 and 2. And remember, these two are degenerate, and I use this degenerate as a basis, and then I construct another new state, which means new basis, which are the linear combination of the original basis. Is that clear? Okay, I'll repeat that again. So initially, at the beginning, we use these two as a basis, right? But these two bases is not good because I have, well, it's not good. And now we know this. Notice that these two, 1 and 2, are the better bases. Why? Because this 1 and 2 diagonalize my Hamiltonian. And how I got 1 and 2? 1 and 2 are the linear combination of the original bases, 1, 0, and 2, 0. Okay? Is that okay? And also the key word, the key is that it goes 1, 0, and 2, 0 in these two bases. In this basis, H naught is diagonalized, right? 即使在旧的这个基底下 ，H0 还是对角化了嘛，对吧？所以 ，so the linear combination, if you use the linear combination, H naught doesn't change. 所以它在这个下面已经是对角化了，所以你再怎么线性组合，它还是对角化，对吧？这样可以吗？它还是对角化。所以呢 ，H0 重不重要 ？H0 根本不重要，不管你怎么做 ，H0 都怎么样，都是对角化的。不管你这边怎么组合，它都对角化的，是吧 Okay, so the important part, the key factor is to diagonalize which part. You choose a good basis which can diagonalize which one? Which can diagonalize H1. Is that clear? Is that clear? OK， 所以重点就是什么？重点呢，你要在原来的这个基底下面找到一个好的线性组合。那这个好的线性组合可以怎么样？可以对角化你的 perturbation Hamiltonian。OK， OK， good. Let's take a break.